So what I'm going to do now is we're going to do an introduction into what physics is. This is section 1-1 in the OpenStax textbook. You should be able to pull it up. If you haven't read it already, no panic. This one's kind of an easygoing thing. It's the ever popular question, what is physics? Why do we do physics? What's the purpose of doing physics? Way, way back when I was in high school, I took a course in physics, and I thought to myself, this is the silliest thing I've ever seen, trying to figure out why bowling balls work. You know, it's so intuitive. Well, I shouldn't say intuitive, it's so common. We all experience it, we all do physics without even thinking about it. Then I got into college and took my physics class in college and got hit upside the head severely because I didn't realize in high school that the motion of the bowling ball, the rules that govern the motion of a bowling ball, are the same rules that govern the moon going in orbit around the Earth, or the throw of a football or a baseball, or why water waves can knock over buildings. All those rules are still there. It's just expanding from something simple to something much, much more complex. So we'll start off. I know what the problem is. There we go. So what is physics? Wow, what is it? Okay. Simply put, well, way back when, it was originally called natural philosophy, because back in ancient times, and in fact not so ancient times, even to the Middle Ages, philosophy was the idea of understanding. Okay? After all, regular philosophy is you're trying to understand why. The concepts of philosophy is why, right? Why are we the way we are? Why do we do the things we do? Why we think the way? What is it? Why is the universe the way it is? I mean, the ever popular, are we really here, or are we just some kind of illusion? That's philosophy. Natural philosophy, though, is the philosophy of nature, the knowledge of nature. First person to actually think about stuff, what scientists refer to as the father of scientific thought, is Thales of Miletus. You don't need to know the names. Don't panic about this. This is just a little history lesson. Thales of Miletus, before the ancient Greeks, when people built stuff, they built stuff to do stuff. They didn't care about the whys and the hows, they just cared that it worked. The whys and the hows was the gods will it. That's the whys and the hows. Okay, that's one reason why Pythagoras, with his Pythagorean theorem, actually made a religion around it, because, wow, look at this, the gods have given us this relationship. Okay? For example, the Babylonians knew about the Pythagorean theorem. Did they ever write out the Pythagorean theorem or prove it? No. They just knew it worked. And how do we know it worked? Because they built buildings with sharp corners. Think about that for a second. What do I mean by buildings with sharp corners? Well, real simple. Pythagorean theorem, you know the a squared plus b squared equals c squared. Okay, here's what you do. You make a rope with a certain length. Now, one length of the rope is going to be 4 units long. The other length of the rope is going to be 3 units long. What you do is you put the mark right there. You walk out 3 units to that point. Then you walk out to this point right here, which should be 4 units. When this length right here when it is taut, and that length is exactly 5 units, you've made yourself a right angle. Now you just put in your stakes, and now you've got yourself a right angle to set up your wall. See how that works out? That's how they're able to do right angles without actually having to do any kind of mathematical proof, no compasses or anything like that. All you need is a piece of string with a total length of 12 units. See? Clever, isn't it? Ancient aliens. Oh my goodness, how come the pyramids were built on foundations that were so flat? How could they make them so flat? It had to be aliens. No, it was water. Dig a hole, fill it full of water. Water's going to have a nice flat level. Mark the edges. Now drain the water out. Now you've got the edges for your foundation there. See? No aliens needed. Let's move on. So Thales of Miletus was the first person to actually think about the whys. He's also the first he's credited with being the first person to predict an eclipse. Legend has it that he was looking up at the eclipse going, wow, this is really cool, and he fell into a well. So, yeah, scientists were absent-minded even back then. Aristotle, of course, we already know. He's a philosopher in the idea of thought. He was also a philosopher in the idea of nature. Now, his ideas of natural philosophy were disproven later on, but they were still influential for almost 2,000 years. We move on to Ptolemy of Alexandria. He's the one who comes up with this model that says, okay, we see the sun is going around the earth. We see the planets are going around the earth. Let's build a model that predicts where everything is going to be at. And he predicted a model that worked. It was clunky as all get out, but it worked. It essentially was, have you seen the teacup rides at Disneyland, or maybe the octopus rides that you see at some parks, where you have a central hub with extended arms, and at the end of the arms you have more arms, and at the end of the arms you have the car. The hub spins, which spins the main arms, but then the smaller arms are spinning as well, and then the carts themselves are spinning. So by adding all the motions of these spins together, sometimes the cart is essentially standing still in real space, and sometimes the cart zooms ahead very, very quickly. Well, that's essentially what Ptolemy's model of the universe was in order to make everything work. Okay, Copernicus went, there's an easier way to do this. Instead of putting the Earth in the center and everything around it, let's put the sun in the center and put the Earth going around it. Now the reason why the planets look like they're zipping past us is because they're like they're overtaking us on a racetrack. That's the inner planets. The outer planets, why does it look like the outer planets are slowing down? Because we're overtaking them. You see, if you're driving along and you have a car next to you and you're passing that car, doesn't it look like it's going backwards relative to you? That's what happens when the Earth passes Mars in its orbit. So it isn't as complicated. Problem was, Copernicus did not have the precision necessary to prove that his model was better than Ptolemy's model. Ptolemy's model worked. Copernicus' model, not so much. I know in chemistry you guys are talking about precision and accuracy. That's one reason. Until you can actually get the measurements to the point where you can see a difference, you really don't know which one's right. Isaac Newton, though, now here's the thing. Nicholas Copernicus is the early 16th century, so we're talking about 1506. Isaac Newton was late 17th century, we're talking 1670. So there's about 150 years. I forgot, there's one guy in between those two, Galileo. Galileo was around 1609, 1610. Galileo, plus a number of other people, Tycho Brahe and Johannes Kepler, they were able to get measurements to the point where they were able to see that the Copernican model of putting the sun in the center actually works better than the Ptolemaic model of putting the Earth in the center. One more minor detail, though, and this is where, and I don't have his name, I should have him there, of Johannes Kepler. Copernicus said that the orbits of all the planets are circular. Kepler was able to prove that the orbits of the planets were not circular, that the orbits were elliptical. They were stretched out. And because of that, then his model matched the actual data that was collected. His model made better predictions than Ptolemy's model. Boom, bye-bye Ptolemy. See how that all works out? Scientific process. Okay, so natural philosophy basically is asking, how does nature work? What is nature, though? What do you say? What do you think nature is? Yeah? Natural laws of the universe. So nature would be the universe, everything. So what does that mean that we're going to look into as far as physics is concerned? Maybe not this class, but as far as the subject of physics looks into, what did we look into? In a word, everything. Okay? Physics is the fun. You're going to hear this so many times. Physics is the fundamental science. Everything is built off of physics. Chemistry is the physics of electrons. Make sense? Okay? Biology is the chemistry of life. And then all the other sciences are based on those interconnections. But everything is still, the fundamental rules of the universe is the realm of physics. Now, the scale of physics, we look at everything. We look at human scaled, which is what we're going to do in this classroom. We're going to take our measurements, things we see, phenomena we measure, relationships we can see, we can make connected through that. But we go down into the microscopic scale because we're asking a simple question. What's it made of? Okay? 3-year-olds are wonderful physicists. They ask the right questions. What's that made of? Well, let's see. Let's go find a Nobel Prize. Let's go get a Nobel Prize and find that answer. Okay? Seriously, it's a Nobel Prize. People, what is everything made of? Molecules. You can follow a 5-year-old's logic from that point. Okay, what are molecules made of? Atoms. Okay, what are atoms made of? Protons, neutrons, and electrons. Okay, what are they made of? Well, the electrons, they're not made of anything. They are what they are. But the protons and the neutrons are made up of items called quarks. Okay, what are they made of? You can keep asking this question over and over again. Eventually, you got to get to an end. And that's where the cutting edge science is going on right now. But we also look at the universe. Okay, how big is it? How far is it? What's out there? Who's out there? Okay, all sorts of scales. And the interesting thing, astrophysicists are strange in the fact they have to take microscopic processes to explain universal, big-size, universe-sized processes. Okay, how does the sun work? Well, there's this subatomic process going on producing heat and light. And that heat and light is producing all these other effects that occur throughout the universe. Okay, I don't know if you can tell, but I'm a little bit excited by it. It's kind of cool stuff. Okay, now here's the key. To try to figure out what's going on in the universe, we have to kind of determine what the rules are. That's really kind of the goal of a physicist, is to determine the rules of nature. Problem is, I cannot do an experiment on a star. See, I know in high school you guys have been exposed to the scientific method because you had to do the science fair and you come up with, here's the hypothesis and here's my experiment and here's the observations and this and that. It's like, but there are times when you either physically cannot do an experiment or you ethically cannot do an experiment. Do you see what I mean? Then what you have to do is you have to learn by observation. The good news is we have mathematics that helps us out, mathematics of statistics. So if I have a sufficiently large sample, I can come up to some conclusions. The tricky part is what causes the changes. Okay? There's a group, tongue planted firmly in cheek, called the Church of the Flying Spaghetti Monster. Now, I won't get into the details of why they were organized or anything like that, but they bring up a very, very important point. One of their tenets is that pirates prevent global warming. How do we know this? Simply put, the heyday of the pirates was the time of the Spanish Main back in the 1700s, right? Pirates everywhere. Now we look in the Caribbean. Do we find as many pirates out there? Not really. We get drug runners and we got smugglers, but we don't have pirates out there. Not as much as we used to. You know what we do have now? A warmer globe. So because we have less pirates, we've got a warmer globe, right? Okay. The Church of the Flying Spaghetti Monster, and again, it is completely facetious. It is not a real thing. They are a joke. And they are aware that they are a joke. Okay, but this points out something very, very important, which is just because that there is something that these two things have some kind of relationship, apparent relationship. Let me rephrase it. It's called correlation. As one goes up, the other goes down, or as one goes up, the other goes up, or whatever the case may be, right? That does not mean that there is a causation. It just may happen that they're totally unrelated, but they parallel each other. For example, I saw one which showed the box office. There's a correlation, about 98%, between the box office grosses of Kevin Bacon movies and the number of people who strangle themselves accidentally in their bed sheets. There is a very, very high correlation. So is Kevin Bacon killing people? Of course not. Okay, so that's the problem we got to watch out, is we got to deduce these rules by observing. And we've got to see, so deducing the rules by observing is like watching a chess game. If you've never played chess and you watch a chess game, you just see these pieces move apparently at random. But then after a while, you start identifying the different pieces, and you start seeing some kind of relationships. For example, you see that the pawns are always moving forward, or that the bishops always land on the same square they start, the same color square they start with. Okay, there's a white bishop and a black bishop on each side. Okay, so after a while, you can deduce the rules of chess. And it turns out the rules of chess are actually fairly easy. Now, being able to play chess, that's a different matter. But that's a different subject. Oh, and by the way, watching chess is still kind of fun until you see something, you think, oh, I've got it down. And then you watch some guys play and you see an en passant capture. If you know what I'm talking about, that's fine. It's a weird capture where the pawns don't actually have to go to the same square. And there's still a capture. And you kind of look at it going, wait a minute, what just happened there? Well, that's where the fun stuff happens in science, when we look at something in the universe and go, wait a minute, what just happened there? Okay. I've got an exercise for you. Mr. Carter, I'd like you to come over here. And here's what I would like you to do. I want you to, these little groups, 2 little groups. I've got these 4 terms. They are not in any kind of order. Okay? I want you to make a hierarchy of which one from the highest is so the first one would be the least rigorous, and the last one would be the most rigorous. So law, theory, hypothesis, fact. Which one is the least rigorous and which one is the most rigorous? And I'm going to do that as a plicker. Okay? So as you can see, for A, 2 would be the least rigorous and 4 would be the most rigorous. So why don't you guys work on that for a couple minutes? Feel free to discuss amongst yourselves. Okay, have you figured out worked up your numbers for your rankings yet? Okay, so I'm going to go ahead and put up the plicker. Okay. Okay. One of the technical thing about the plickers, for it to work, it's got to see white space around the symbols. So if your fingers are overlapping, it won't be able to see the code. Okay? So what we have here is something that's not too unusual. Okay? A number of you are saying, some of you say a theory is the least rigorous. Some of you are saying a hypothesis is the least rigorous, but really what you're doing is just flipping the two of those around. But then number 3 would be a fact and number 4 would be a law. Okay? That's how you rank them. Scientists rank them this way. Okay. And now that means we need to have a little discussion about, so what we're looking at is we're looking at a hypothesis, a fact, a law, and then a theory. So let's have a little discussion about the meaning of those words. Okay? Okay, so as I said, a theory is the most rigorous. And now I'm putting it in vertical. A theory is most rigorous, followed by a law, followed by a fact, followed by a hypothesis. Okay, so let's discuss this. And let's get these definitions down. All right? I understand why you chose the way you are, the orders that you did. Because people speak a different language. Lay people speak a different language than scientists. Okay, so let's start off with a hypothesis. We can all pretty much agree that a hypothesis is somewhat very low on the rigor scale. But what is a hypothesis? A hypothesis is a tentative idea. Okay? Some say a scientific guess or an educated guess, or there's all sorts of different names for it. But a hypothesis is kind of the thing you want to say is, well, what we got to do is we got to have it being able to be false. Okay? I can't say something for a statement to be a hypothesis, the opposite must be capable. Okay? All right? Okay, so everything gets pulled to the earth. Is that capable of being false? And the answer is yes. All you got to do is put a not somewhere in there. You can either say not everything gets pulled toward the earth, or everything does not get pulled to the earth. Either one of those is a contradiction of the statement that I made. Of course, that leads to a different question should it turns out that's the case, but you see where we're going here. Okay, so you have in statistics what's called the hypothesis, the thing you're going to test, and the null hypothesis, which is the outcome if your thing is incorrect. Or I shouldn't say incorrect. Okay? There's not really an incorrect when we're talking about science. Okay? You know, when Edison invented the light bulb, and by the way, Edison inventing the light bulb was a major achievement, don't get me wrong. But technology was at a point where somebody was going to invent the light bulb. It just took somebody that was going to be willing to do the work. So Edison kept having all these failures and was asked, is this going to put you down? It's like, no, I know what doesn't work now, so I can move on to something else. Okay? So let's move on. What else? Must be testable. There's a key thing. Just because it's wrong, or just because it's capable of being wrong, does not necessarily make it a hypothesis. We have to be able to test it. Now, some hypotheses we can't test just because it's physically impossible. Okay? But theoretically possible would make it a hypothesis. The alternative, of course, is a speculation, which means something you really can't test. Then it's a speculation. Okay? And hypotheses must be observable. Okay. Now, what's a fact? I put the next thing as a fact. And again, this is where a lot of people say, well, facts are the most rigorous thing. Well, not quite, because what facts are observables. Things we can all agree upon that happen. Okay? So if I take a pen and drop it, we can all agree upon the fact that the pen fell. Do you see what I mean? Okay. But we do not know why it fell. We know the fact. Now, many facts, the good facts, are the ones that are repeatable. Okay? And they should be measurable. So if I take a pen and I drop it, I'll go, wow, cool, pen fell. Let's do it again. Wow, pen fell again. All right, there may be something here going on here. Let's see if we can get some measurements for it. We take out the stopwatch. How long did it take for the pen to fall? Let's take a look at the pen as it moves. What happens to the speed as it moves? You see, we start getting more information on it as we complete our measurements, as we get different kinds of measurements. But again, all we know, though, is that when we let go of the pen, it falls. That is an observable fact. And it's important to know, for example, in the law, you have statements of fact. When the lawyers come in, it says, here are the facts. Okay? How do we know that they are facts? Because we have the evidence that shows that they are the facts. Okay? For example, a fact. It is a fact that we find blood drops at the crime scene. Okay? Do the blood drops belong to the killer? We do not know. We cannot make that as a statement of fact until we can make some kind of connection that connects the two together. You see what I mean? Okay. So you got to be careful about taking a fact and leaping it to infer another fact that hasn't really been tested or confirmed yet. A fact is not an observation, or not an explanation, excuse me. The pen falls. Great. Why? Don't know. Just know that it happens. See what I mean? Facts are often called laws as well. Actually, I'll talk about laws in a moment. Okay. I'm sorry. A fact is an observation. A law or a principle is a relationship that has a high degree of repeatability. So, for example, I could say that if I take an object and drop it and let it fall, it will fall. That's my fact. Okay? Then, as I continue to measure it, I notice something. That is to say, how hard it gets pulled depends upon how far away it is from the planet. Okay? That's another fact. That's something but I'm starting to see a relationship there. So there's a law or a principle there. Okay? Often it's a statement with a relationship. It is not an explanation, though. The moon goes around the earth. That's a fact. The period of the moon going around the earth is a certain period. That is also a fact. The period of the earth going around the sun is a certain amount of time. That is also a fact. But we see, if we make the assumption that the same force that pulls the earth to the moon is the same force that pulls the earth to the sun, and we see that the relationship between the sun and the earth is the same kind of relationship as between the moon and the earth. You see what I mean? They share the same relationships. Now, why does that relationship exist? Why does gravity exist? My principle does not give me the answer to that. Oh, and by the way, is it 100% accurate? Oh, heck no. Okay, there are all sorts of laws out there, scientific laws, that are merely just observations that happen with a high degree of reliability. The ever-popular Murphy's Law, for example. Okay, by the way, the original Murphy's Law, not the one we use, which is, if anything can go wrong, it will. The original Murphy's Law was actually stated by an Air Force captain who stated if there are multiple ways of doing a thing, all the wrong ones will be done first before the right one gets done. Does that make sense? Some of you may have had that experience. There's also another one, it's a social science law called Godwin's Law. It actually predates the internet, but it shows up. It showed up a lot when the internet message boards came up, and he came up with it in the late 60s, which says that any discussion, any argument, if left to its own devices for a long enough period of time, will eventually bring a comparison to the Nazis. Anybody who's ever seen a message thread, a thread on, say, Reddit or something like that, doesn't everything always eventually get to the comparison to the Nazis? Even if we're talking about Macs versus PCs. That was way back when. Okay, so is it a law? Yeah, it's something that happens with a high degree of probability. Why? Oh, I don't know. Okay, and laws and principles are relatively simple statements. Okay, they can be the beginning of the scientific process. Okay, the statement that, hey, we see this relationship between the moon and the sun, we see between the moon and the earth, and we see this relationship between the sun and the earth. Okay, great. Why? What is the mechanism by which this happens? That's where we get to a theory. Now, what y'all did is you ranked a theory relatively low. To a scientist, a theory is relatively high on the rigor. It's not really rigor. I mean, that's probably the wrong word for it. Instead, what we are looking for is an explanation. And that's what a theory is. A theory is the explanation. Okay? A fact or a law or principle gives us the what happened. The theory gives us the why it happened. You following along now, guys? And now you see why they're two different things. A theory is not a hypothesis. A hypothesis is a prediction. From the prediction, we do the experiments in order to get the observables to determine the facts. Once we get enough facts together, we see what these relationships are between these particular facts, and then we can come up with some tentative explanations. That's where the theory comes into play. Okay, see, the theory is based on observables. This is connected to this. There's this relationship. When I increase this, this increases, or when I increase this item, that item decreases, or something like that. There's some kind of observables. If we can put it in a mathematical form, it's even better. Okay? It must be capable of being changed. Here's the difference between a scientific theory and a lot of other theories. Okay? Scientific theories, because they're based on observables, you have to change the rules as you play the game further on. We're playing a game of chess. You make a hypothesis, the game proceeds, you see the move, you go, oh, my hypothesis is correct, so therefore I'm going to deduce that the rule is this. Now I've got an explanation. The explanation is I have to play this way all the time. Then something strange happens, like castling. In chess, that's when when the king and the rook exchange positions. That is a break, because your hypothesis, your initial theory could be you can only move one piece at a time and you alternate moves. Now you do castling, two pieces are moving at the same time. Does that mean that your whole chess game goes out the window? Does that mean your whole theory of chess goes out the window? The answer is no, it does not. It means you have to modify it to include this new event that occurred. You see what I mean? Theories are not thrown out just because of one or two contradictory facts. It could be your theory is not complete. Okay? So the other thing is the theory has to be capable of being wrong as we get new facts. The best example that I like to use is the heliocentric model of the universe compared to the geocentric model of the universe. Okay, the heliocentric model, the geocentric model, the Ptolemaic model of the universe worked. It worked right up to the point where it didn't. What I mean to say is, based upon the observations at the time, the model worked. It made predictions, the planets ended up where they were supposed to be, and everything was all fine and hunky-dory. There were a few little glitches here and there, but, we got to tweak it a little more. The Copernicus model, where everything was in circles, well, that worked as well, but not as good as the Ptolemaic model. So do we throw out the Ptolemaic model? Not necessarily. It makes more sense from an aesthetic standpoint. The simplest moves are probably the correct, but until Galileo made observations, until Brahe made observations that showed that this model was better than that model, you really couldn't throw the other model out. Once the observations came in, it's like, okay, out the door, we don't need it, consign it to the dustbin of history, to misquote Marx. Okay? Make sense here, guys? Okay. By the way, beware of a scientific theory beware of a scientific theory that says, here's my theory, now here's my facts. It should be the other way around. Here's my facts, now here's my theory that explains the facts. I like to say that it's the case of believing is seeing, right? I have a theory. Aliens did everything. Now I can look for facts that match my theory. You see where I'm going here? That kind of turns it around the other way. Okay, must be verified by other researchers. Wow, I saw this wonderful thing. It really works great. It's fantastic. Okay, I'll go ahead and do it. I didn't get it. Well, you didn't do it right. I didn't get it. Well, you're in the wrong place. I didn't get it. Well, you didn't say the appropriate words or invoke the appropriate demon or whatever the case may be. You see what I mean? If other people cannot confirm it, then your theory is not really proved, is it? Oh, and by the way, theories are always being reviewed because theories always have holes, or they've always got room to grow, if you will. Okay? They can be very complex to explain many different aspects. In some parts of it, it's relatively simple. For example, what's called the standard model, which is what everything is made of. Everything is made up of quarks or leptons or bosons, and these items, I mean, I know a bunch of words that went by, but the problem is that while we have a theory that explains matter and energy pretty well, there's still another question of what are those components made out of? And that's where it's all fuzzy, if you will. Okay? That's the edges. That's where the theory needs to be expanded. So the end goal of the scientific process, then, isn't to collect facts. It's to model outcomes. It's to try to determine theories, to determine the rules of nature. Theories are the rules of nature. And by the way, one more little detail. Don't get caught up in that word theory and make it think, oh, it's just a tentative kind of thing. Okay? These lights work on the theory of electricity. Modern science is based upon the theory of atoms. The stars are in place due to the theory of gravity. You see where I'm going here, guys? Okay. All right. So I've got an exercise for you. We're going to do some more plickers. What I'm going to do is I'm going to, first of all, on the video, what I'm going to do is I'm going to pause this so we can do the plickers exercise. I will show what each of the exercises are on the slides, though. Okay? So what I'm going to do is I'm going to ask you a question by giving you a statement. And you have to determine whether or not it is a law, a theory, a fact, or a hypothesis. I've only got 2 minutes left. I want to point out one more little detail, one more thing we do. In science, what we do is we like to build models. Now, models represent some kind of physical principle. They can be physical models like a globe or a map. Does a globe tell us everything about the Earth? No, it just tells us information that's on the globe. So the problem with models is they're not going to tell us everything about everything. They're only going to tell us detailed stuff about a particular aspect, a small thing. Okay, there's mathematical models, which are a series of equations. In fact, we can make our physical models based upon the mathematical models. That's called computer-aided design, right? Computers take the equations and use those to make the physical models. Models are not complete, okay? I can take a look at a globe, and it can tell me political lines, or it could tell me elevations and depths, but it's not going to tell me like what's inside the globe. See what I mean? It's not the end-all and be-all for geology. Okay, and now I'm just going to go over these real quick. These are my exercise here. Teapot exists halfway between the Earth and the Sun as a hypothesis. Interest rate spending cuts, there'll be a decrease. That's a hypothesis. Molecules are formed by the attractive forces between electrons and atoms of the atoms. That's a theory. That's the atomic theory of chemistry. Objects tossed into the air will return to the Earth. That's an observable, so that is a fact. And there exists a force between electrons, the magnitude proportional to the product of the charges, inversely proportional to the square of the distance between them. That's a mathematical relationship, isn't it? And if it's got a high degree of reliability, we can go ahead and call that a law. That's called Coulomb's law right there. We'll see that in the second semester. Okay, we'll talk more about the scientific method. I've got an activity for you guys on Tuesday, Thursday, where we will actually practice using the scientific method. Okay, that's all I got for you guys. I will see you guys next time.